Hello everyone and welcome to another Intro to Signal Analysis video. Today's topic is the division of complex numbers. So let's get going. Alright, so the example that we're going to solve today is to divide these two complex numbers, z1 and z2, and they're defined right here. So we're going to find another complex number, z3, which is z1 over z2. And we're going to solve this problem two different ways. We'll do it first using polar forms and then using Cartesian forms. Alright, so we notice first of all that z1 is in polar form and z2 is in Cartesian form. So we need to do some quick conversions to get z1 in Cartesian and z2 in polar if we're going to do this calculation. So let's get going with that. So first we're going to convert z1 to Cartesian. So that's pretty straightforward to do. We write z1 we know is going to be equal to, well, this is the radius of z1, 12, and this is the angle of z1, or pi over 4. So we can write z1 is going to be equal to 12 cosine of pi over 4. That's the real part of z1. And then the imaginary part of z1 is 12, the radius, times sine of pi over 4. And so cosine and sine of pi over 4 are easy to remember, so we can just convert them. This will be 12, we can pull the 12 out of both. Cosine of pi over 4 is square root 2 over 2, and sine of pi over 4 is square root 2 over 2. So we have our converted z1, which is now in Cartesian form. Alright, so that's straightforward. Now let's convert z2, this number here, to polar form. Now one thing we could do, we could almost immediately recognize, well, this looks very similar to this, with the exception of the sign of the imaginary part. So we expect that z2 is also going to have an angle of pi over 4, but because of the negative sign of the imaginary part, it's going to be minus pi over 4. But we can actually go through and solve this in a slightly more formal way, and that's probably a good idea to do here. So z2, first we can solve for the radius. The radius is just the square root of the square of the imaginary part, of the real part. So 3 root 2 over 2 quantity squared, plus the square of the imaginary part, which is minus 3 root 2 over 2 quantity squared. And then we can rewrite that, and that's going to be, well, we can pull the 3 out of either, 3 squared. Square root 2 over 2 squared is going to be 2/4. Square root of minus, or square of minus root 2 over 2 is 2 over 4. So the radius is just 3. It's the square root of 3 squared. Okay, so that's the radius, easy to compute. And the angle, theta, is the arctangent of the imaginary over the real. So of minus 3 root 2 over 2, that's the imaginary part, over the real, which is 3 root 2 over 2. So it's the arctan of minus 1 over 1. I'm keeping the sign here associated with the numerator, so that tells us which quadrant it's in. And we know that the angle that has the arctan equal to, or the tangent equal to minus 1 over 1 is minus pi over 4. That is in the fourth quadrant. So we can rewrite z2 is going to be 3e to the minus j pi over 4. So now we've converted both z1 and z2 into their respective Cartesian and polar forms. So now our goal is to compute z3 is equal to z1 over z2. And this is easy to do given that we've got both of these in polar coordinates, so let's just write it out. It will be 12 e to the j pi over 4 over 3 e to the minus j pi over 4. Okay, well, it's easy to see that we're going to first divide the radii, and we're just going to get 4 out of that. And then we can move e to the minus j pi over 4 to the numerator. And we'll have e to the j pi over 4 plus pi over 4. Because when we move this to the numerator, we're going to add its exponent. And so we have our final answer. Z3 is equal to 4 e to the j pi over 2. That's in polar format. We could sketch it in the complex plane. The real part is on the x-axis and the imaginary part's on the y-axis. And when we do our sketch, I'll sketch it in red here, 4 e to the j pi over 2 is this vector, where it's got a length of 4, and it goes around here by pi over 2, so it's on the imaginary axis. So that is our answer. Z3 is equal to 4 e to the j pi over 2. That's our answer in polar form. So now let's see if we can obtain the same answer when we do the solution in Cartesian form. Okay, so here we're going to get going. I've written out both Z1 and Z2 in Cartesian form. And so now we'll go ahead and get started by just writing Z3 is equal to Z1 over Z2. So I'm going to write out the Cartesian forms here. 12 root 2 over 2 plus j root 2 over 2 over 3 root 2 over 2 minus j root 2 over 2. Now first what we can see is we can go ahead and just divide the 12 by 3 and we'll get a 4 in the numerator, so we can just reduce that right away. So we'll get 4 times root 2 over 2 plus j root 2 over 2 over root 2 over 2 minus j root 2 over 2. Now we don't want to leave it in this form because we want our final answer to be in the form a plus jb, so just a real part plus an imaginary part. So in order to get that, we're going to go ahead and multiply the bottom by the complex conjugate. So let me just illustrate here. I'm going to take the complex conjugate of the bottom, so square root 2 over 2 plus j root 2 over 2. These two are complex conjugates of one another. Now I don't want to change the overall expression, so I have to put this thing in the numerator as well. So I'm going to multiply by root 2 over 2 plus j root 2 over 2. So overall, here I'm just multiplying by 1, so I'm not changing the overall expression, but it is going to help me reorganize the expression. So let me go ahead and just reduce a few things. So I've got the 4, and that's kind of out front. Now I'm going to do just multiplication by doing basically the FOIL method on these two factors here. And so I'm going to get root 2 over 2 times root 2 over 2 is simply 2 over 4. And then I've got root 2 over 2 times j root 2 over 2. That'll be plus j 2 over 4. And then I've got the other factors, right? I'm going to multiply j root 2 over 2. So that's another plus j 2 over 4. And then I've got root 2 over 2 times, oh, sorry, j root 2 over 2, whoops, gotta get rid of that. I've got j root 2 over 2 times j root 2 over 2. And that'll be a j times j is minus 1, so that's going to be minus 2/4. And then I'm going to write over this, I'm going to multiply these two together, so I'll get 2 over 4 for this, and then j 2 over 4. And then minus j 2 over 4, and finally I'm going to end up with a minus j times a plus j, and so that's going to be plus 2 over 4. Okay, so hopefully that makes sense. All I'm doing is multiplying each of these factors out, and now I'm just going to add them together. So up top here, the 2 over 4 minus 2 over 4 are going to cancel each other out, and I'm going to be left with j times 4 over 4, which is just 1. So I'm going to be left with 4j in the numerator, and then on the bottom I've got 2/4 plus 2/4, that'll give me 1, and then these two terms cancel. So on the bottom I have 1. So I'm left with just 4j. Now remember from the previous slide I got z3 is equal to 4e to the j pi over 2, which was, whoops, if I draw it in the complex plane, it was here at 4j, because that's the imaginary axis and that's the real axis. So I've gotten exactly the same numbers, exactly the same answers as I got using the polar form. Okay, so if we look back at these two answers, you can kind of decide which one's easier. Probably, for this example, the polar solution appeared to be easier, but it may not always be easier, and that's it may be difficult sometimes to convert Z1 or Z2 to polar form. In that case, you want to be able to go through this Cartesian solution, which is pretty straightforward. All we did was basically multiply by the conjugate of the denominator over the conjugate of the denominator, right? So we multiplied by a factor of 1, but that allows us to rearrange and get a solution in Cartesian form. So that ends our video today. If you want more information about the course that this video was made for, you can check out the websites. You can find the course website under my own website. And this is the department website, the School of Engineering website, and more information about George Mason University. Thanks for listening.